When we've talked about dispersion of plumes, we've used a D, and we've said, okay, that's the dispersion that we're going to use in our differential equations. But there are two processes which give rise to dispersion. One of them is diffusion, and one of them is hydrodynamic dispersion. Okay, so we have these two things. So when we talk about the classical diffusion, and this is something that actually Einstein was really material in developing understanding, you basically have a set of molecules in space, and they all have energy, and they're all vibrating. And so in time, this plume of compounds will inexorably spread. And it's the passage of time gives diffusion. And diffusion, it will happen whenever time passes, things will diffuse. Dispersion, on the other hand, is very different. Dispersion is when we have a media, let's say, and we're going to push our solute through that medium. And so what's going to happen is that if we start with solute in this form, as the water flow pushes the solute through, then this is going to deform. And so we're going to end up with, at time 2, this is going to be at time equals 0, at time equals 1, it's starting to bend, and then at some point, this is going to be deforming all throughout this system as it has stagnation points and high velocity points, so the plume is actually getting sheared apart. And that's hydrodynamic dispersion. So what do we see is different about this? This occurs with a passage in space. So hydrodynamic dispersion is a function of how far something's been displaced, not how long it's been there. So there's two fundamentally different processes which we wrap up in a single D, and I'll often write as a double back with a 3 there, and that I will call the joint hydrodynamic dispersion, which is going to be a function of diffusion plus dispersion. So I will call dispersion a double back D, and I'll put the 3 under it and call that the sum of the two. And so that would be the types of dispersion and diffusion that we have. And what we do then is we draw what's called, we calculate the Peclet number. And what it is plotting is the effective hydrodynamic dispersion over the diffusion. So at low Peclet number, this has a value of 1, which means that this is equal to that, so that just it's diffusion dominated. So when things are going slowly versus fast, and then as we cross a Peclet number of 1, then this curve bends up. And we get more and more contribution to the spreading process due to the hydrodynamic processes. So a typical Peclet number curve will look like this. This can certainly get into values of hundreds times greater than diffusion or whatever. It can go really quite high. And so when we are solving the problem of moving solutes, we first have to really identify, gee, are we in the low Peclet number where diffusion is the dominant process, or are we in the high Peclet number where we have to consider both diffusion and dispersion?